I could take out so many things, but I mean, you have to kind of tolerate me in case I get little longer this time. Yeah. All right, so let's get started. This is already 12:25. So maybe I was supposed to stop at 1:30, but maybe around up to 2 o'clock it may continue, something like that. So this is the topic that was told to me. In fact, I was given a free hand for optimal control in general, and I thought I will talk a little bit about some development in our lab and also associated kind of tutorial part of it before that, so that everybody feels connected basically. So let's get started. This is the topic, title of the talk, Nonlinear Real-Time Optimal Control using Model Predictive Static Programming. That's the terminology. And then if time permits and all of you are okay with that, and then we can continue something on optimal guidance of aerospace vehicles. And this is a very lot of similarity with autonomous ground vehicles as well, including autonomous cars, because there some things are in 3D and some things are in 2D. Relative advantages, drawbacks are there as well. All right, so let's get started. And before we do anything, acknowledgement to my institute. And of course, it doesn't need any introduction. It is named, but still, it's kind of a summary. We have 40 departments, 4,000 students, 500 professors, and we roughly about 2,500 publications per year. And of course, #1 in the country in research performance. And of course, we are known for predominantly graduate studies. That means masters and PhD. We have very little undergraduate program. Our main focus is masters and PhD basically. Founded in 1909, more than 110 years old, but still we are pretty young. In the sense, a lot of young people make the institute always vibrant. And it never sleeps. In the night also we work, day also work. Everything is very good working environment per se. So this is the institute that has given me space, given me opportunity to kind of think, stay, and explore various things, and has given me a free hand to explore whatever I want. So a big acknowledgement to my institute. Those of you who, I mean, if there is any graduate students or something, I mean, you are planning for your masters and PhD, probably this is the right place to think about as your first priority. And the name tells you science, but we are equally good at engineering as well. That's the only comment that before I move on. All right, so now fast forwarding to my lab. Here, this is one slide summary of what all goes on in my lab. I can see we've worked on missile guidance, a variety of them, both air launch, surface launch, and things like that. We've also worked a little bit on bio-inspired guidance, which is like formation flying, autonomous landing, things like that. I've got formation flying on satellite. We'll touch upon it today, and I'll talk a little bit about this. And this is one of the closest problem to our heart, which is Chandrayaan-2 landing mission of ISRO. So we all know what the outcome happened, but still it is worth taking you through that journey a little bit. Time permit. And then we have got this interest in autonomous, I mean, guidance of this UAVs, autonomous, unmanned aerial vehicles and all that, both fixed wing as well as rotary wings. And also we have got interest in this laser weapon system or guided laser systems they call, directed energy weapon they call nowadays. It is getting a lot of limelight around the world. Our country also started something, we get involved in that. We have also worked a little bit on nonlinear and adaptive control of high performance aircrafts as well as hypersonic vehicles, things like that. And this was our journey for a reusable launch vehicle of ISRO. And we have some contribution towards this recent HSTDV mission of for DRDO, especially the launch vehicle part of it. Before the hypersonic vehicle per se starts flying, you have to kind of launch it from a launch vehicle and get the right initial conditions for that, and that is where our contribution is at. Well, this is all about aerospace, but however, we are also interested in biomedical. This is one major activity that goes on in our lab. Today, I'm not going to talk about it. This is feedback control for customized drug delivery, and that's a general topic. But within that, we talk about a large part of it is actually automatic insulin delivery for type 1 diabetic patients. That's what we are getting ready for clinical trial also, first round, probably early next month. And then we also have some interest in the neuro control of eye movement. So that is how the brain activity happens and things like that. I'm not going to get into all that. We have some interest in process control as well. And all of these, whatever you see here, we have publications to back up. It's not just interest and all. We do get involved in various programs, projects and all. Eventually, we'll end up with some publication or multiple publication, things like that. That is how this has happened over last 20 years. So let's move on, and then my area of interest is largely both theory and applications, but I will rather say it is application driven theory rather instead of theory driven application. In other words, we start with some sort of application and then try to apply some theory. If it happens, well and good, but most likely it will not happen. Then you think about what all we can do for theoretical, like extension of boundary and things like that. So we get into the theory part, then extend the theory, and then come back and solve the problem. So that's how the development has happened over last several years. And today I'm going to talk about optimal control and predominantly on some guidance aspects of aerospace vehicle. And that is how we'll start actually. The motivation for getting into nonlinear optimal control will be derived from several guidance problems of aerospace vehicle. And that is, you see optimal control, there are some 3-4 branches of engineering as well as mathematics have contributed in a very big way. Of course, mathematics has contributed in a very big way, and mathematics department, mathematics professors have contributed a lot. But if you talk about engineering, electrical engineering, certainly yes, but mostly into stability theory and things like that. But then nonlinear control, nonlinear optimal control has been propagated extensively through aerospace engineering, and now it is. To extend it even further, process control and all. I think chemical engineering has also contributed quite a lot. So aerospace engineering, chemical engineering, electrical engineering, in fact, all of those autonomous, right now the so-called cyber physical systems, all that. That is where you will talk about a lot of uses of optimal controls. So that is where we are interested in. And research funding, I think you heard about it. I'm not going to talk about too much of that. So this is how this journey of our lab has started. And today I'm going to talk a little bit about some journey which I have done through this IISc collaboration. The outline of my talk is I'll start with some sort of a motivation, and then a little bit brief overview of optimal control so that everybody feels connected to the system or connected to the talk. And then what is real-time optimal control? That also some motivation will come to that. And then I'll some touch upon something that we discussed that I just initially told about this model predictive static programming that that is predominantly a development in our lab, and that is how I'm going to take you through a little bit overview of that. More on that, you have to kind of go through that study and then publications and all that. I will list a few publications as well. And then next will be MPSP guidance for aerospace applications, and I'm going to talk a little bit of lunar soft landing and something about formation flying of satellite. I'm not going to take you through that extensive thing, but I'll just tell you what the summary of the results is, and eventually some concluding remarks as well. That is how this today's talk has been scheduled. Let's start with motivation part of it first. First, let us talk about guidance of missiles. That is where a lot of aerospace engineering people who wanted to contribute to the guidance of missiles have explored this optimal control theory in a very big way. In fact, when I was a DRDO scientist way back in 96, 97, and that is where a lot of publications came to my attention, where it was mainly optimal control based guidance and trajectory optimization, all that. So I was very curious to kind of explore it further, and of course, the life has given me the right opportunity to explore that in a better way, deeper way, basically. Now, what is guidance of missiles, by the way? Now, those of you who don't know guidance of missiles, it is the missiles never hit the target, by the way. It is just for information. Missiles never hit the target physically. All that they do is they just fly by. I mean, one target is going, a missile will go fly by. And then whenever you are closest, then you take a warhead and then kind of explode it yourself. So obviously you will be destroyed, but at the same time, the target is also close by. So both the missile and target get destroyed. So that's the whole concept of missile guidance, basically. Now the concept is if this is the separation, then of course that is what the closest distance is called miss distance. That is the distance by which the missile will miss the target. Now to minimize the miss distance is what is the primary objective of missile guidance. In other words, if you can really take it very close to that target, then your effectiveness of a warhead will be very high. So of course, what people talk about in missile guidance, the very first thing is very small or near zero miss distance. So that is going to be the first priority. There is no compromise on that at all. Yeah. But things have moved on. I mean, this is not traditional warfare anymore. So now people started demanding more and more and more because of war game and superiority and winning conditions and all that issue, right? So what is the next criteria? Anyway, so anything that you talk about guidance missiles, your very small or near zero miss distance has to be there. Right? This is something like our cell phone purchase and all that. If you want to buy a smartphone, then of course you look for camera, voice quality, because I mean Bluetooth, all sort of things. But then the very fundamental thing is every phone that I select has to have communication well. So in other words, I can actually talk to the other fellow well. I mean that's the first condition basically. They know a smartphone is of no use if it talks all sort of things, but I'm not able to talk to another fellow, right? So that is the first criterion, first priority, and hence this silencer missile, the very first priority, invariably it is there, either hidden or explicit. Either you call that as explicit or implicit, it is anywhere there. Now the question is what is next? Okay, after that, what is there? So we talk about well minimum control effort now, because what happens is the moment you have too much of turning, like a snake sort of thing, if you go, then what happens because of the turning kind of behavior or turning path or things like that, your projection area becomes much more for projection of the missile surface with respect to the airflow. I mean that's what that is where the drag comes. So it turns out that it actually induces some drags, extra drag basically. So in other words, if you do not do this kind of too much of maneuver, too much of turning and things like that, you go in a relatively kind of straight line sense. Of course, it will not be straight line, but minimum turning sort of thing. And then of course you'll end up with minimum drag basically. So that is where if your drag is reduced, then of course you save energy, and with that you can actually talk about going further, right? So your range will be high and things like that. Right? So that is where minimum control effort actually needed for minimum induced drag as well. And also, if you can do your kind of job with minimum control, then even if you start with a very bad initial condition, you can still go ahead and capture the target, right? Because your control effort is still available. If necessary, I can turn better, right? So that means it will also give you not only minimum induced drag or maximum range and things like that. We'll also talk about larger capturability. In other words, even if I am not favorably placed initially, but still I can turn better and then go and capture the target basically. So that's what it is, the minimum control effort. Is it everything? Of course not. We still, after this 1 and 2, the demand is still more. And they talk about, well, now what about impact angle constraint, right? It is not good enough to go towards the target in a kind of straightforward manner, because target is also not dumb these days, right? They are also having target defense mechanism and all that. They are also looking for who is coming to attack me and all that sort of thing, right? So you want to kind of defeat that, then probably you have to turn around, go back, and backside you come and all that, right? So that kind of a thing which will give you some sort of a heading angle constraint sort of thing. Number one. Okay? Number two, suppose you want to talk about some sort of your target is a tank or things like that, then of course the tank is very heavily protected from the side. If you attack from the side, hardly anything happens. But if you attack from the top, then that is the most vulnerable place actually, right? At least there is some place where the pilot has to go and sit inside and drive the tank basically. That's kind of thing. So that is where you have to really, if you want to talk about kind of attacking a tank, then you have to go up and then come straight vertical basically. So that is where your top attack that's going. Okay? Similarly, you can also talk about front attack. Right? There are many issues like that. So it doesn't matter how you come, but eventually when you attack, if you attack from front, it attack from top, attack from side, and things like that. Actually. So that gives you some sort of impact angle constraint as well. Is it everything? Of course, there are more. And then now you talk about, well, throughout my journey, I should not miss the target, basically, right? Because if I miss the target, then I may not be able to capture it back again. So throughout the path, I will talk about now look angle constraint. In other words, my own seeker, which is like onboard radar sort of thing, which should continue to look at the target. It should never miss it, basically. And then, there's something called salvo attacks. That means 3, 4, 5 missiles will come different places. They will start and things like that. But target is same. They will take their own path, but eventually when they attack, they will attack everything together, sort of thing. Right? So it is not one later. Not that will not be that effective. It will come together. Some sort of they start from different positions and all. They somehow kind of coordinate and then go together and try to kind of attack it. So one is the same time impact, and the other one is same time and same position impact. And then third one is same time, same position, and same angle impact. So there are many things that we now talk about in missile guidance, which is actually not traditionally when you start with something like only zero miss distance or something. That is not everything basically, right? If you go with such a dumb guidance law which ensures only zero miss distance, then it is very easy for the target to nullify the missile also basically, right? So that is why we all talk about all sort of things where you talk about smart weapon and things like that actually. So these are the problems where this classical guidance theory may not be very good in some sense. As for each of the issues, the classical guidance theory, which is simply inspired from geometric observations and things like that, they may not be sufficient. So that's the message. Similarly, go to the guidance of UAVs. Then what we first talk about in guidance of autonomous unmanned aerial vehicles. First is waypoint navigation. Well, I start from somewhere and then go to point A, point B, point C, and then come back to my where I started. Right? So that is kind of waypoint navigation. Very first thing. Then we talk about, well, automatic takeoff landing. Now, even the waypoint navigation, what happens is normally your takeoff happens through a pilot, and when you land, there also that is piloted landing basically, because there are autonomous issues and all that. Most of the time the UAVs get lost otherwise. But then can you take out of that, because the real power of UAVs will come with only when you make it completely autonomous flying as much as possible, right? Because the numbers has to be large, and hence piloted vehicles are not possible anymore. Pilot means the pilot really doesn't sit on the UAV, but the pilot is actually driving the UAV from the ground basically, right? Through the RC remote control and things like that. All right, so waypoint navigation is not everything. Now we talk about, well, can you do automatic takeoff and landing? And then the next one is terrain and collision avoidance. That means when you start flying from point A to point B, or instead of whatever the mission is, in between there will be collision chances, right? There may be bird flying, there may be another UAV, there may be something like, there may be a tall building, all sort of things that somehow you have to avoid and then start flying, basically, right? It may be directly on your flight path. If you just go from point A to point B to point C in a straight line way, and then all these may be obstacles for you. And these are all static obstacles. But as you fly, there may be the heavy birds and all that. These are dynamic obstacles, basically, right? Another UAV flying by, so that is also dynamic obstacle. So all these things has to be sensed and avoided, basically. You have to sense it and then talk about some degree of either coordinated or uncoordinated maneuver, depending on whether the target is cooperative or uncooperative, and then carry on with your mission, basically. Then what's the fourth one? You have to now talk about coordinated flights with ground vehicles as well, and there are many applications for that. For example, like some criminal is flying away, basically, right? He has done some crime and it is just driving very fast and things like that. So of course, your UAV should continue to track it and then to continue to give that information to the ground station police and all that. So this is just one crime prevention. There are many other things, actually, right? For example, if your UAV wants to kind of land on a moving ground vehicle, basically, then ground vehicle is also moving. It cannot stop because there is emergency. Let's say the UAV has to land on some sort of ambulance, basically, right? The ambulance is on a mission. It cannot stop for the UAV to land and then go, basically, right? So it is going, and then ambulance. The UAV has to kind of coordinate with the ground vehicle and then come and land on the ambulance, basically. So there are many applications like that when you can think about. And similarly, you can now talk about formation flying and cooperative missions as well. So you can see that how these guidance problems are becoming more and more challenging, more and more interesting in that sense. And then you really need more and more better toolboxes to handle all this. Now, what about space vehicles? Suppose we talk about spacecraft. Of course, we will also talk about very first thing that we talk about station keeping. That means the satellite has to keep on orbiting on the intended orbit. That's called station keeping. Then you talk about formation flying, like 2-3 satellites can they coordinate one behind the other or side by side and things like that. Of course, remember, satellites cannot fly side by side because they have to fly on orbits, and each of the orbit has to be planar, and each of these planes has to contain the center of Earth, basically. That means if one orbit is like this, and this is the plane of the kind of orbit, then another one is like this. That means this has to be the plane. So even if one is going like that and one is going like this, they are still under formation. This is how your GPS constellation is actually done. 24 satellites flying like that. All right, and then you talk about, well, radar docking. That means one satellite is going, the another one will come very, very close and then try to kind of dock it. And there are several applications for that. Of course, you can transfer some fuel so that increase the life of the satellite, or you can talk about debris removal, like it will go capture something and then come back and then throw it to a different orbit altogether, so that that space gets empty. Especially for those geostationary orbits where the things are pretty crowded now and these satellites are very heavy. So now you go with another one and then kind of grab that fellow and then they kind of deorbit that. So that space becomes empty, basically. So the many planning, many operations are there where you need this radar docking, and this is actually a mission for ISRO also. There is some activity that is coming up very soon. And then you talk about, well, autonomous landing and autonomous landing on extraterrestrial bodies, like what we saw that in Chandrayaan-2, like going to moon all the way and landing there, or next day maybe going to Mars and landing there, going to say asteroid landing there, things like that. And remember, these are not something that there are nice landing pads available, right? Not even a helipad is available. Forget about the airport actually. Right? So there is nothing there. So in other words, you have to really kind of figure it out where to land, where is my safe area, where is not, and all that. So while you are approaching the landing place, then your attitude also is somewhat similar, somewhat conducive, so that your sensors can look ground and figure it out where to land, where not to land, basically that kind of thing. So all these problems, what you see about, we will talk about lot of attitude control problem. Okay, so attitude means how that satellite is oriented, basically that kind of thing. So all these problems will come with a lot of attitude constraints periodically or continuously, either way. And then you talk about they will come with state constraints, they will come with control constraints, they will say there will be control optimality issues, there are sensor error issues, there are many things that keeps on coming. So what you see that in control theory basic course, when you start applying to certain things, there are many things that we normally don't get exposed to in the traditional control theory courses as well. So these are the problems that you now talk about, and then to go back to what you need to do and things like that. Now, if you see all these problems that you saw, then guidance of missiles, guidance of UAVs, guidance of spacecrafts, and things like that. This I'm a predominantly aerospace engineer, so I can think about all that. So all these problems you cannot now talk about classical conventional guidance things. So now we talk about some better theory which will kind of give me some sort of a platform where I can actually think about solving these problems properly. That's the whole motivation. So what are the typical challenges to solve it? Well, first of all, you got terminal constraints, and there nowadays it is not sufficient to ensure only position. Now you have to ensure velocity as well. That is where you get this impact angle constraints will come through the velocity vector direction sort of things. That's called aspect angle constraint in some sense. So at the end, when the problem is over, at that point of time, not only your position has to be desired position, but also velocity vectors should be also desired orientation, I mean, the constraint on the velocity vector should also be met. And off late, there are constraints on acceleration also that is coming, basically, right? So now we'll see that in our Chandrayaan mission and all that, which I'm going to talk to you a little later. We'll also, I mean, we'll come across that there is a problem with both position, velocity, as well as acceleration quantities. I mean, their constraints needs to be met, basically. So traditional now it has gone to velocity as well as acceleration level as well. Now still people talk about jerk level, which is actually rate of change of acceleration. That we are not going to talk about here, but that actually gives you gives kind of some sort of mechanism as well. All right, now next one, control has to be minimum. We talked about it. So minimum control solution, that means from T0 to TF, your U square integral has to be minimum. That's U square dt T0 to TF. If you take that way, then that is the minimum control solution. And that leads to enhanced range and larger capturability, things like that. And then now talk about path constraints. We discussed about look angle constraints. Throughout the journey, I should not miss my target. And then we talk about maximum altitude constraints. For example, if you're talking about some sort of a cruise vehicle, I mean cruise missile or whatever, cruise vehicle, whatever we're talking about, then if you really go to very high altitude, then your lift may not be sufficient. So your vehicle will drop off. It will drop down. And if you really go to very high altitude, even though there is high velocity and your lift is good and things like that, you can kind of argue. Then what happens? The very purpose of this mission is compromised. Right, the whole idea of cruise missile is it will fly as close to the surface of the ground as possible, so that the satellite cannot detect me, right? And the ground station cannot detect me long. I mean, if the ground station is situated long away, then the Earth curvature comes in. No, I cannot be detected. And if it is detection from satellite also, because the reflected signal will be very close to ground, and hence both the signals will go at the same time. There will not be too much of a difference, actually, right? That's the whole idea of cruise missiles and cruise vehicles and all that. So if I go too much of a high altitude, even though I can continue to fly, the mission is going to be compromised, basically. So that is where it is not advisable. What about multiple vehicle missions? We talked about formation flying salvo attacks and things like that, simultaneous attack, what I mean. And then there are issues of sensor inaccuracy as well. None of the sensors are actually very accurate. And now you can do some sort of a state estimation, and that is where your Kalman filter and other things comes into very handy. But also remember that no matter whatever filter you kind of implement, irrespective of the best ever Kalman filter, whatever it is, there is also something called Kamara bound and all sort of things where you can never estimate things in a very accurate manner. There will be residual errors, basically, right? So now the question is, if there is a residual error, given enough computational power, Can this guidance, what you are talking about, handle that? What sense it will handle? At least now it can talk about, well, instead of a point or the physical vehicle position going wherever I need, what I need to do is now, well, because I've got residual sensor errors and all that, I will now talk about some sort of expected value of that. In other words, whatever the residual errors, take about expected value, and that expected value will go and engage with the target. But that is not everything. Expected value or average value is not everything. Now you have to talk about not only my expected value will engage with the target, but all the variation that I'm talking about around that expected value is going to be minimum, basically. So in that sense, we have got some results which actually is very promising. This talks about, well, I may be deviating little bit midway, but ultimately when I engage wherever I want to go, then that point of time the accuracy is quite good, basically. But that demands a little more computational power, of course, basically. So these are something that you now talk about. So what is the summary? Now, after all the discussion, the summary turns out that, well, there is classical guidance laws and there are these so-called optimal guidance laws. And many classical guidance laws are actually inspired from just observing nature, and they are typically not very quite effective for challenging problems. People do actually work on enlarging some of these constraints and kind of relaxing constraints and cater for some of these things, but still they need a lot of assumptions, and especially many of the literature, if you see, they are typically in 2D, and typical our aerospace doesn't fly in 2D. It is, I mean, obviously always 3D, basically. That is one thing. There are many other things which actually doesn't talk about. Simply observing the nature and doing that is probably not very quite effective for modern warfare, especially in modern challenging problems in all sort of missions, basically what you talk about. So hence optimal control theory happens to be a very natural tool, because this optimal control theory is something that you can talk about nonlinear system dynamics, you can talk about terminal constraints, you can talk about path constraints, you can talk about inequality constraint, equality constraint, all sort of things that we talk about in optimal control theory. So far, whatever we saw the problems, that actually if you just think a little bit deeper, then optimal control theory happens to be a very natural tool to obtain very effective guidance laws, and that is what is called as optimal guidance laws, essentially. Okay. So in that framework also, now that, because now you talk about linearized system dynamics versus nonlinear system dynamics and things like that. So the moment you talk about linearized system dynamics and just quadratic cost function and things like that, typically it leads to some sort of a closed form solutions. In other words, we don't need to do this numerical solutions as we go along, basically. Right? So that is one of the advantages, and that is where this kinematics or linearized dynamics based guidance laws have come into literature way back, I think 40-50 years back, basically. Right? And people still are fond of that, and that is one of the guidance laws we call general explicit guidance laws and all that. That is still used in many of our own missiles in DRDO as well. Actually, right? So, but that is a very recent development, which actually talks about linearized kinematics, but still it is capable of giving you some sort of impact angle constraints and things like that. So that's the reason, basically. But having said that, in general, if you really talk about very intelligent target, it is maneuvering sharply and things like that, it is trying to engage with you and you want to engage with them, all sort of things, that kind of a thing. And that's the situation, this kind of thing may not be very effective either, basically. So then what is effective? Of course, we should not be afraid. We should really go to nonlinear optimal control theory and then try to solve this nonlinear optimal control problem as it is, basically, right? And that will eventually lead to very effective approach, and that holds the key, basically. So why nonlinear control? I mean, I already summarized a little bit, but just to kind of re-summarize again, if you want to call it that way. And the variety of difficult real-life problems can actually be formulated in the framework of optimal control. And here I take a little bit detour in the sense, even though I'm talking a lot of aerospace here, remember we also worked on process control, we have also worked on biomedical control and things like that. These are nothing to do with aerospace control. I mean, the generic theory part of it is very much applicable with whatever field that you are working, basically. So if you are an electrical engineer, you find out your own applications and try to solve it. In fact, one of our papers also talks about our power system control and all that, using knowledge optimal control. Okay. Anyway, so coming back, a variety of difficult real-life problems in whatever engineering field you are talking about can be formulated in the framework of optimal control, because it gives you a platform where you can talk about what to minimize, I mean, explicit way of representing a cost function, and it gives you some sort of a system dynamic constraints towards the path. It also talks about inequality constraint, that is the safety constraints and all that what you're talking about, right? Or my physical reality issues and all that. So because of all this capability that that optimal control gives us, that is why it has become very powerful tool to solve a variety of difficult real life problems. I talked about it enough. State and control bounds can be incorporated in the control design process explicitly, right? You don't kind of struggle for tuning, and then somehow getting it done and then proving it through a lot of simulation. And we're not talking about any of that. Okay? You need a state and control bound, either state control or mixed state and control bound. That has to be there, and that you formulate as part of the problem formulation and leave it to the solver to solve it for you. Okay? So that is what you're talking about. All right. Now, the incorporation of optimal issues can lead to a variety of advantages, and that is something like explicitly we can talk about minimum time or minimum energy or minimum control, whatever it is, actually, right? That is how we'll construct your cost function, and that actually gives you a direct advantage also as compared to other control theories. Okay? So, in general, what you call is trajectory planning issues can be incorporated into the guidance and control design, which is none of the other control design approaches will typically give you this advantage, and that is why nonlinear optimal control is extremely powerful, by the way. Okay, so what is this optimal control? Optimal control we are talking so many times about. Let's talk about a little bit overview of that theory itself, and then we'll come back to some sort of difficulty and how to avoid it and all that. So before you do anything, try to pioneers of optimal control. It's really not new. It started in 1700s. It goes all the way to Bernoulli, Newtons, and things like that. But later on, very strongly formulated through Euler and which happens to be a student of Bernoulli, and then later on with Lagrange and all that. Euler was somebody who actually formulated in discrete optimal control, and then Lagrange kind of put that in continuous time framework. But then when you take delta t tends to 0, and in the limiting sense, both happens to be equal. And that is why now this theory is called EL theory. In other words, both of them have never done that theory together, but because both leads to the same thing, is very famously known as the Euler-Lagrange equation, basically. But then people realize that, okay, these things are too complicated in mathematics. And remember, that's an era where not even calculator was there, slide rules were not there, nothing was there. Everything you have to do, not even graph sheet. I'm not very sure about that, basically, right? So you have to keep on doing a lot of math, and eventually you have to talk about what is the interpretation out of that. And then it turns out that even for simple problems, they have to do some 5-6 pages of mathematics. But when the complicated problem starts, they have to give up, right? So it was everybody realized that this is a good theory, a good concept, but of no use in practice, basically. So they all left, actually, right? So that theory got a little bit of death in some sense. But 200 years later, in 1900 especially, this person, if you see the picture here, the Pantriazin single-handedly kind of revived this field, and he was exploring this constraint optimal control. In that process, he systematically done, he kind of made this theory entirely systematic, actually. Right? So a large part of this systematic discussion of this theory actually goes to Pantriazin. Yeah? So what he call as Hamiltonian, that necessary conditions and all that will come through this Pantriazin's analysis. And later on, Bellman and Kalman and all that have also contributed. So they all contribute. Pantriazin, Bellman, Kalman, all that you see, it is 1900 essentially. And Kalman is somebody who contributed a lot of things in LQ theory, the linear quadratic theory, both in control as well as estimation and things like that. Bellman is Hamilton, Bellman, Jacobi, and all that you see that. So the Hazelby theory, something that dynamic programming and all that is various contributed. So this is how this theory got revived last century, and then a lot of it gave us a lot of new insights. And by that time, the computers started coming, and then computer speed were improving day by day like that. So now a lot of things can be done, which 200 years before it was not possible, basically. So a lot of people have actually started realizing potential of this field. And not only the realizing the potential, this was actually got implemented also in many of these aerospace vehicles actually to begin with. The first lunar mission, that Apollo mission and all, that is where it got the first usage of onboard computer basically in a big way, in a space mission especially. Then Cold War is also another area where people want to kind of superpower each other and all that, right? That is where they don't mind spending little bit of new technology and a little bit of money and things like that. So the Second World War and followed by Cold War has given this field a lot of push basically. But anyways, let's continue the journey. So this is what the pioneers of optimal control, if you want to call them. But there are a host of other people who have actually contributed to this theory, and the theory is pretty rich by now, basically. All right. So what is optimal control? An optimal control problem formulation consists of several components. Then one of the first component is performance index. You really construct one performance index that needs to be optimized. We call that as again minimum time or minimum control or minimum energy or minimum whatever it is. That is something that the designer has to kind of select it depending on the need basically. Now people also talk about hierarchical control and all that, right? Like something you need in inner loop, something you need in outer loop, something you need in further outer loop, all sort of things, right? Those of you who are aware of this MPC, now the model predictive control and all, they talk about economic MPC now, which is nothing but in aerospace language, it is actually what we traditionally call that as guidance theory. So now economic MPC, what people talk about in process control domain is almost very similar in my view, is what we call as guidance in optimal guidance in aerospace engineering. So which typically operates in outer loop basically. All right. So after the performance index, we also need to have this appropriate boundary conditions. So we now talk about like initial condition, final conditions, and both can be either hard constraint or soft constraint. Both ways. I mean, you can now talk about well, what is hard constraint by the way? Like suppose I want to kind of go to a particular place, and that particular place is the one. I don't want to land somewhere else, somewhere here and there, basically, right? So I will talk about only that particular place is my constraint. In other words, my final position should be equal to a desired position, sort of thing, basically. So those kind of things are, but the hard constraints are typically difficult to meet, and that is why a lot of times we now talk about soft constraints. In other words, even though I want to go there, anywhere close by is all right, basically. Okay? So that is where you talk about some sort of a error ball minimization, rather than becoming very adamant that no, I want my control thing. I mean, I want my control thing to behave in such a way that my exactly I should go there and then nowhere else, right? So these are the give and take of hard constraint versus soft constraint. Hard constraints are good from the mission point of view, but soft constraints are good from the solution point of view, basically. Right? So after this performance index and boundary conditions, now you really talk about some path constraints. And first thing first is system dynamics constraints. So whatever system is there, with respect to that, you need the solution, right? So if I really have a kind of a very big, let's say, bus or something, I cannot drive it like a bike, basically, right? A bus is the properties of the turning radius of the bus and all that is very different from turning radius of the bike or auto, whatever it is, right? So if I really want some sort of a kind of a navigation through the road, then if I'm driving a bus, then I should get a solution. If I'm driving an auto, I should get a solution for my auto, basically. That kind of thing is called system dynamics constraint. So depending on whatever system you are talking, then accordingly you now talk about the corresponding system dynamics. And then in addition to that, you can now talk about state constraints. Like if I'm driving a vehicle, my vehicle should never fall out of the road. So road boundaries are becoming my physical boundaries all the time. And then control constraint, well, if I'm got a steering wheel or whatever, I cannot keep on steering it forever, right? My wheels can turn maximum something like 45 degrees this way or 45 degrees that way. So only that way I can turn basically, right? So those kind of things has to be put as control. So optimal control formulation consists of three major ingredients. One is performance index, followed by boundary condition, and followed by path constraint basically, which can be several variants in several forms and all that. So depending on the need, we now formulate and solve and propose appropriate solution actually. Okay. Now going ahead, we have this performance index mathematically. This is a very famous form. It's called Bolza form, and this is something like a terminal penalty, and this is something like path penalty, which happens to be inside the integral. And then you have got path constraints in the form of system dynamics. Then boundary conditions. So typically, your initial conditions known, and final conditions can be free. Free in the sense there will be some sort of a desired condition, and error balls will be minimized. I mean, that is how we will formulate the problem. And this free condition typically goes here in the form of a quadratic ball to be minimized, basically. Okay. In other words, x of tf square, if I put it here, then of course all that I want is x of tf has to be as close to 0 as possible. That kind of a meaning, basically. So we'll talk about typically TF is fixed, so TF can be free. Okay, that depends on the problem formulation, but most of the time, if you concentrate on this kind of a problem formulation, then many of the problems are actually taken care within the framework, basically. Okay, so that's the meaning. That is no way that you cannot solve. I mean, it doesn't mean that you have to confine within that. In other words, you can now talk about x0 free, that's still possible. TF free, certainly possible. I mean, x of TF constraint, hard constraint, that is also possible. So various combinations are certainly possible here. But if you confine the problem formulation to within this, what is displayed here, then it leads to there are various approaches and solutions and all that is proposed. There are variations about that. Let us try to understand how do you solve this problem basically. Formulation is not everything. You have to now talk about solving it. So when you try to solve it, there are various approaches that are available. One is called indirect approach and one is called direct approach. An indirect approach is the one which comes from the CL equation, that Euler-Lagrange and all that. That talks about variational calculus approach. And eventually it leads to this so-called necessary conditions of optimality followed by sufficiency conditions. And depending on the situation, you may or may not use the sufficiency condition. So that is called the indirect approach. Whereas direct approach is two ways. One is dynamic programming. You just solve one equation and if you're able to solve, or there is something called transcription method, where you can now talk about divide rule sort of concept. You put several time grids on that, and then depending on the time grids, a lot of time grids and all that, and then you discretize the entire problem. And at every time grid, you have got that many variables to kind of solve for and all that. So in other words, you are transcribing this entire optimal control formulation, which is actually a dynamic optimization formulation, into some sort of a static optimization framework basically. So once you transform this dynamic optimization problem to static optimization, you can solve that static optimization. In the process, you will get a solution out of that. So that is the whole idea of transcription method. So there are these three approaches, and very quickly let us see that each of that advantage, drawback, and all that. And if you really follow this calculus of variation approach, the first one, this will give you some sort of conditions like this. And those of you who have a little bit of exposure on this optimal control can very quickly see what is going on here. So it will give you the set of necessary conditions of optimality. And one of that happens to be the state equation, which is, or we started with that as a constraint. Then followed by this is co-state equation, which will first to define Hamiltonian, and Hamiltonian is something like L plus lambda transpose F. And what is L? L is coming from this side, and F is coming from here. So L plus lambda transpose F. And what is lambda? Lambda is called co-state variable, and lambda dimension is same as F dimension, the system dimension. So lambda transpose F becomes a scalar. L is anyway a scalar because J happens to be a scalar. So you construct this Hamiltonian like this, and then come up with this necessary conditions of optimality. So what gives you state equation, co-state equation, optimal control equation, and boundary conditions. Now what is happening here? To solve a problem of n dimension, you have introduced this variable lambda, and that is also giving you some sort of a differential equation also. Differential equation, right? That means what happens? You've got n for n dimensional problem. Now the problem has become 2n dimensions, right? N from here and n from here. Okay? So that is what that is not end of the story. If you just look at it, well, for state equations I've got initial conditions. Whereas for co-state equation I've got final conditions. So it is not possible that I can start with a set of initial conditions and either I propagate backward and either propagate backward or forward. It is not possible to do that way. So now you talk about a lot of this guess solution and going kind of back and forth. Eventually you'll solve kind of merge somewhere, and that is happens to be a solution. Right? So if you just look at it very closely, because of the split boundary conditions, in other words, n conditions being initial condition, n conditions being final condition, this problem is called the 2-point boundary value problem. So your boundary conditions are given at two different points of time, basically. Okay. So that is what is known as this, and eventually there's much more into this. What turns out is the state and co-state equations are dynamic equations, and whereas this optimal control is actually a static equation here. And out of these dynamic equations, not only the boundary conditions are split, their behavior is typically opposite. Right? If your state equation is stable, the co-state is unstable, and vice versa, like that actually. Okay? So this is what happens here. So state and co-state are dynamic equations. If one is stable, the other one is unstable. Optimal control happens to be a stationary equation. Boundary conditions are split. That leads to 2-point boundary value problem. And the state equation develops forward, whereas post-state equation develops backward. That is because of the boundary conditions. Initial condition is known for the state, so you can march it forward. Final condition is known for the post-state, so you have to march it backward and all that. So the numerical methods are designed by keeping all these thing in mind actually. Okay? So traditionally, these two-point boundary value problems demand computationally intensive iterative numerical procedures, which lead to open loop control structure basically. So eventually, even if you solve all that, you are solving for this particular x naught that you are talking about. The moment that x naught is something different, their solution is not valid. And that is why your solution happens to be, even after doing a lot of hard work like that, it happens to be an open loop control structure basically. Okay? So this all that thing is known as curse of complexity. Okay, so I think what happened there? Somebody has put that end or hello?
Yes, sir.
Yes, sir. You are audible, sir.
Audible, but what happened? The slide sharing stopped, right?
Yeah. Yes, sir. Audible. Sir.
But slide sharing
Sir,
stopped.
no
So I have to
problem
put
at
that
all.
again.
Sir, audible, sir.
Okay, fair enough. Okay, slide is showing. I mean, the slide is okay.
Sir, please continue, sir. Sir, audible, sir.
All right.
Everything okay, sir. Everything okay.
All right. Okay.
Slide
So
not
this is
visible,
known
sir.
as curse. Slide is visible.
Now
Yes,
it is
sir.
visible, sir.
Yes, so the
Okay,
slide
perfect.
is visible and you're audible.
Perfect. Okay. All right. So it is known as curse of complexity, basically, right? So all these things are not really that easy to solve and all that. So because now you are talking about solving a particular value of initial condition, now people thought about, well, can I not get a state feedback solution, basically, right? Then I don't worry about it. Whatever is my state, my control will be ready for that. Actually. That is your typical linear system E equal to minus kx sort of thing, basically, right? So that is what you want to do. And that motivation leads to the state feedback optimal control solution. Eventually, it is very simple. It relies on some sort of a fundamental theorem, which tells you that any part of an optimal trajectory is actually an optimal trajectory. For example, if I want to go from point A to point B, and this happens to be my optimal path, then I cannot have a second optimal path actually, right? So that's what it tells. The reason being, my integral, whatever T0 to Tf, I can put a T1 in between, and the integral becomes split actually, right? T0 to T1 and T1 to Tf. Now, if T0 to T1, if this was optimal, this is the cost function is minimum compared to that guy, I mean this path, then I should have actually taken that path. But then this is the optimal path by definition, of course, and then because of that, this is actually not possible. So this is very fundamental theory, very fundamental kind of observation, which tells you that any part of an optimal trajectory is an optimal trajectory by itself actually. Yeah? So using that, and all of you are welcome to see the theory and all that. And I mean, there are many places to latch onto this theory. And of course, there are many good books as well. And those of you who are interested to see more, you can actually always see my NPTEL lectures also. I've got a full-fledged optimal control course about 40 lectures on that optimal control itself, basically. So anyway, so this is going through that process. You can come up with this equation, which is called Hamilton-Jacobi-Bellman equation. So now you define your optimal cost in such a manner that, okay, this optimal cost has to satisfy this. And see, lambda is del v by del x. And now you talk about this guy to be equal to 0. So of course, it leads to this nonlinear coupled partial differential equation of n plus 1 dimension essentially. So obviously, this approach has some advantages. Of course, the resulting PDE is typically very difficult to solve in general. And of course, it also leads to this huge computational storage requirement as well. And all these observation is summarized nicely by Bellman himself, which calls curse of dimensionality. In other words, if your T0 to Tf happens to be larger, or your dimension of the state becomes more and more, then this actually the complexity of computation actually grows exponentially. So that is where the curse of dimensionality has come. So this is one side, it is curse of complexity, other side is curse of dimensionality. So what about the third one? I talked about transcription method. That is where you discretize the problem. So state equation you discretize using, let's say, Euler integration approach. Cost function you discretize, let's say, trapezoidal rule. These are very simple numerical schemes and all that. And then pose an equivalent static optimization problem and solve this problem using static optimization method as well. Right? So that is the whole idea, very simple idea of transcription method. And this essentially leads to this so-called MPC, model predictive control. Okay? So because these are very standard things, and of course this will lead to a lot of huge computational issues and all that. People thought about how to reduce complexity of computation, and there are many improvements on that. First of all, higher number of, okay. First of all, how to improve the results, right? You talk about, well, I can talk about improving the results by taking large number of grid points, right? My delta t can be smaller and smaller, so my grid points are larger, but I will have a better solution actually. But so then we now talk about, well, that may not be a very good idea because it leads to the dimensionality of the optimization problem very, very fast. It grows in a very fast manner. So what is the other way? Well, I can talk about better approximation of the state dynamics by using higher order finite difference approaches. Euler integration, I will leave it and I'll go to the higher order part of it so that I can use the higher delta t and larger delta t. So typical examples are these Runge-Kutta methods and all that. And also people talk about polynomial approximation between segments and all that. Different segments will have different polynomials actually. Yeah. Then a better approximation of cost function. Similarly, you can have higher order approximation, you can have quadrature approximation, things like that. But what is a major problem? The fundamental problem is eventually it leads to a large dimension optimization problem, and hence computationally it becomes very inefficient. And not only that, it typically gets trapped in local optimum. I mean, that is what the biggest headache of static optimization, right? The dimension of the problem becomes more and more, very likely that you will get trapped in a local minimum. So the solution is never good, basically. So convergence issues do come in and all that. So these are major problems essentially. So, but having said that, the philosophy has been exploited very heavily in model predictive control. So fast, this is something like fast transcription as much as possible. So they talk, well, I'll talk about finite prediction horizon. I'll not take too long and all that. T naught to TF, the TF itself will be small and all that. That's I can do that way. And even after that, I will take a much smaller control horizon. In other words, 2-3 steps, I'll assume that control has stabilized and all that. So these are typically good for regulator problems. So that, I mean, because eventually you are talking about a set point regulation. Everything has to go and merge there. So it well, 2-3 time window later, I will my control has like that's what you can assume. Well, eventually it will happen, but initially it will not happen. But that's the assumption that you go ahead with actually. Now some people talk about input-output prediction. They avoid the state dynamics completely. They go to this so-called AR mix and NR mix and AR mix and all that actually. So these are something like to input to output prediction altogether. Even forget about AR mix and all that. You can still talk about transfer function basically. Right? You go for transfer function from input to output, and then convert that to dynamic whatever the dynamics of output with respect to input. So not bypassing the state altogether basically. Okay, so that is how to kind of reduce the dimension. Then people bring in this sparse algebra. Okay, there are a lot of zeros and all wherever it is there. I will not deal with that. I will talk about the sparse algebra part of it so that I can do certain computation quickly basically. Then people do mesh refinement. In other words, start with a larger grid, a larger delta t. I solve that quickly. And then starting from that solution, I will refine the mesh. Like let's say I reduce the delta t by 2 and I resolve it. And after that, I can again reduce the delta t to delta t by 2 and keep on doing that until I'm happy. Until the solution converges. So these are ideas that that can help us in doing model predictive control in a better way, basically. Okay, so all these things, whatever so far so good. So far, in a very nutshell, we saw this optimal control entire thing. Whatever happens in a sky view point of view, some sort of a bird's view. So what it gives us the impression now is no matter whichever approach we get, either we come from calculus of variation or from dynamic programming, or from, by the way, programming means optimization. It's nothing to do with C programming or Python programming and all that. In optimization, we call programming means optimization essentially. Okay, so you talk about either calculus of variation or dynamic programming or this transcription method leading to MPC and all sort of things. Invariably, even though the formulation is very good and very capable and all that, invariably they'll end up with a lot of computational issues. So, and hence the question is, well, can it be done in real time, right? Whenever the plant is operating, can I really do this, do a solution basically, right? That leads to the question of real-time optimal control. So what summary of difficulties I told you already. Calculus of variations lead to this open loop structure and curse of complexity. And dynamic programming, it leads to huge computational storage requirements. It's curse of dimensionality. And then transcription method, invariably it leads to large optimization problems. And computational turns out to be very slow, local optimum, all that. But having said that, there is one approach that is gaining somewhat momentum is something called pseudospectral transcription. It's a very nice idea. It talks about some sort of a spectral solution, which is using these basis functions and some sort of a collocation points, which are typically not grid points, but we need those points, limited numbers and things like that. So they do a lot of dense algebra with limited number of grid points, and then using this basis functions ideas and all that. So essentially, your solution becomes much faster. But still, it is not very sufficient. I mean, very fast, so that you can think of using in aerospace applications. It is okay in doing some sort of a kind of chemical process control and all that. Probably okay because you've got ground computers and the process itself is slow and things like that. But in aerospace application, that is still not. I mean, in onboard computer sense, it is still. Sometime back, they actually use this spectral transcription for International Space Station. So-called zero propellant maneuvers and all that, momentum dumping and all. I'll not get into that, but essentially they have done it for that way. But then also remember the space problems are typically slow varying, number one, and also they did not do it on board basically. They collected all the errors and all the information, whatever sensors and data and all that to the ground through telemetry, solved it in the ground super fast computer or whatever. Then they uploaded that link, that control solution. They uploaded basically. In that sense, it has done. I think about 12 years back, they have done that. But having said that, we still need very fast computations and all that, so that we can think about using that in onboard processors and that. So, what is real-time optimal control? Formally speaking, question is, can this computational difficulty be avoided so that optimal control design can be useful for real-time application? That's the question that you are asking. And the answer turns out to be yes, and there are several things. So first thing first, a lot of electrical problems and all the regulator. I mean, why electrical? We will also talk about cruise control in aircrafts and all that, right? That is where you talk about LQZ control, where it is LQR control and Kalman filter is state estimation basically. Yeah? So LQR is certainly a possibility, and then extensions of that are SDRE methods, CTRE methods like that. But these are all infinite time problems, remember that, and they're typically good for regulator problems, basically. Then there is a class of solutions called adaptive control method, which is adaptive critique methods, which is neural network based and all that. And then there is the pseudospectral method, model predictive control, especially the fast variants of that, fast MPC. And then finally, we're talking about model predictive static programming, basically. This is a development from our own lab. So let's go through that a little bit further. And what we are talking about here is nonlinear optimal control in real time. Efficient algorithms and advanced processors have to come together and do a very good handshaking, basically. Now, advanced processors have become quite advanced rather. Now we talk about cell phone processors are very capable than our even desktop processors, I mean, just about 15 years back. But having said that, these are something called NP hard problems and all that, whatever you are talking about. Right? So advanced processors are not the solutions for the problems that you are talking about, basically. So processors will help us certainly, but it can elevate the load by only about 30%. The rest of the 70% typically should come from efficient algorithms, essentially. So algorithm itself has to be efficient, and then solve that using advanced processor. You'll be having it is possible to do that in real time now. Basically. So that is what you are talking about. So a brief overview of our approach, we call it as MPSP sort of thing. Motivation first, we want very high computational efficiency. So online solution in real time is possible. That's the very first motivation. Then terminal constraints will be met as hard constraints. Remember, hard constraints are difficult to solve, but we want to solve it in hard constraints using this approach. So that is how the motivation started from a practical problem, basically. No linearization of system dynamics. We don't want to do kind of solve for a linearized version of the dynamics, even though the process may demand that we do repeated linearization and all that. That's a different story. But eventually, the solution that you're talking about should be valid for the nonlinear system dynamics as it is. That's what it means. Then cost function. We started with control minimization problem. That is typically easier because you deal with a quadratic control variable and all that. And after that, you have extended to several things basically, right? So now minimum control usage, minimum deviation from prefix control history, minimum control update, all sort of things you can talk in the control variable sense basically. But having said that, off late you have relaxed that constraint completely. Now your cost function can be a function of state, control everything basically. Right? Then generic, which is kind of a very generic formulation and should be applicable for many problems, no matter whether it is mechatronics or aerospace or chemical or electrical, whatever it is. we should be able to apply it basically. That's our idea there. So now let's go back to our problem formulation. We'll not take the, because we are talking about a hard constraint in the sense of output here. We are not going to take a terminal penalty in the cost function basically. So this is only integral, nothing there outside the integral sort of thing. Then stated output equations are nonlinear. State is nonlinear equation, output is also nonlinear equation. And what we need is that y t equal to tf, my actual output y should be equal to y star, which is actually known to me. You can think that as a target position or whatever, and my own missile position has to go and hit the target basically, right? So that will be equal to that basically. So this theory has been inspired from model predictive control as well as approximate dynamic programming, to both the things. And first publication happens to, I mean, we were successful in publishing this in 2009 basically. After a lot of struggle, of course, some 2 years of struggle and things like that. But then the story was different after that basically. All right, what is MPSP algorithm then? We start with some sort of a control history, propagate the system dynamics, compute the output, and check for convergence. In other words, what is our objective here? We want y equal to y of t equal to y star. That's what we want. This is a known quantity, and this is something that is coming out because of my initial conditions and because of the control history that I applied to the system dynamics, basically, right? So I start with a control guess, and my initial guess of the state is anyway known to me. So I propagate this state equation forward, and then figure it out at what is my y of tf, right? Because at every point of time I can compute my y as well. So at final point of time tf, I can compute my ty, y of tf, and then find out whether it is equal to that or not. If it is not equal to that, I call that as non-converse control, basically, right? So it is not converse. Then I have to go through this. But if it's converse, right? And convergence need not be in the form of only output. That by, even though we started like that, it just so happens that when your output converges, your cost function also converges. And off late, what you are doing is we check for both the convergence. We don't check only for the output convergence. We also check for cost function convergence. Okay. Now, obviously, if you start with any guess, it is not going to give you that. So you have to really do this iteration actually, right? So in the iteration process, it demands that we compute some sort of a sensitivity matrices, and then using the sensitivity matrices, we compute this control history update, and this control update history goes on and on and on like that. Now, somebody can ask, what is the big deal about it, right? I mean, any typical classical optimal control algorithm is typically based on this, actually, right? That is what very obvious. In fact, shooting method is a typical classical example of that, basically. Right? But the beauty part is this loop that you are talking about is lightning fast. It's very, very, very fast. Okay, so this loop is extremely fast, and there are reasons for that why it is fast. Okay, reasons for fast computation happens to be a static co-state vector. I mean, eventually it is not a co-state. We are able to solve it using so-called Lagrange multiplier. You know that. And the Lagrange multiplier dimension is same dimension as output vector. It is nothing to do with the number of grid points actually. Simply deal with what is your output vector dimension. That's what it matters. So the dimension of that is very small, and it is just a static vector. We do not have a differential equation for that basically. And of course, there is a dimensionality reduction that goes on. And then third reason is the sensitivity matrices that you are talking about. They can be computed recursively, and eventually it leads to closed form control update basically. So these are some of these reasons why it is very, very, very fast. And of course, application sense, it has been applied to missile guidance, it has been applied to launch vehicle guidance, reusable launch vehicle, lunar subplanning, which I'm going to touch upon a little bit today, and the formations flying satellites, I mean satellite formation flying, or whatever you talk. Many, many things has been done, and I welcome all of you to experiment yourself also basically. Okay, those of you need it, I can give you the basic MATLAB function for that, which I have written myself basically. The basic MPSP that we are talking about, the extension versions and all, we are not ready for that. I mean, problems have been solved, but it has not written in a generic functional forms so that I can distribute to all of you. But the basic version that I'm talking today is available. Any of you are interested, I will write to me. I'll give you that. So what is this overview and all? Well, let us keep it for the time's sake. I'll not get into that, but eventually this math is available somewhere. So I mean, I'm going to skip it because it's going to take a little bit of time. There are many interesting things to talk after that actually. Yeah? So eventually, the algebra is the salient points for the regions of computational efficiency. Again, let me repeat. Co-state variables have become static. So there's no more a co-state variable, theoretically speaking. All that we need is only a constant Lagrange multiplier to solve the entire control history update. Okay? And the Lagrange multiplier is a very low dimension, has the same dimension as output vector. And these are computed, the sensitivity matrices that are required for these computations can be computed recursively. Eventually leads to closed form control update. Remember that it's not closed form control itself. That will be remarkable, but this is just an iterative algorithm where the update happens in closed form as long as you do not have path constraints, by the way. The moment path constraints kick in, this inequality constraint, this closed form update behavior is not there basically. In other words, we cannot talk about doing this closed form control update in presence of path constraint. That happens to be a kind of an open to name is so good and all that actually. In general, what happens actually? So, right, in general, what happens? The requirement of a good real-time optimal control algorithm. What are the requirements here? Any good real-time optimal control algorithm should first talk about convergence. It should converge no matter what it is, right? So that first that is where the optimal it should converge to the right optimal solution basically. And you can actually demonstrate that using some small benchmark example problems. You know, some of our papers actually talk about that as well. Yeah. Then when it should not only converge to the optimal solution, it should converge in minimum number of iterations. And not only that, each computation requirement for each iteration has to be minimal, right? Now, number of iterations can be minimum, but each of the iteration, if it talks an hour, then defeats the purpose again, basically. Right? So it should actually not only have minimum number of iterations, but computation requirement for each iteration has to be very minimum. Then only it happens to be a good algorithm, basically. And of course, there has to be repeatability and generality so that it doesn't, I mean, one problem you are able to solve, the second one it doesn't work, third one it doesn't work. That is not a good one. The repeatability and generality should be there. And I'm very proud to say that our NPSP has all of the above, basically. So it does converge, it actually does converge to optimal solution. In fact, you are about to submit a paper where you talk about formal convergence analysis and all that. It apparently it is nothing but the sequential quadratic programming. It writes on that proof basically. That's it. And then minimum number of iterations, it actually requires computation for each iteration is minimal and all that. And what I mean is minimum number of iterations in all the problems that you have solved, it has never crossed single digit, by the way. It is always converged in 3 iterations, 4 iterations, maximum 6 or 7. That's all. Okay? And that is the beauty that you're talking about. And because it actually converges in 6 or 7 iterations, now we can talk about something called the iteration unfolding. That means you don't have to remember 6 iterations to happen, right? It doesn't mean anything. You just converse, just compute one iteration, update it, go to the next one, and then compute the next one there, then go to the next one, then go to the next one, like that. So that means your computational requirement is all that you require is just about 1 or 2 iterations at every grid point of time. So that because time of computation is very critical here. And that actually works without compromise at all. I mean, we can invariably show that both of the approaches are pretty similar to each other, basically. As long as that actually works, provided your number of iterations happens to be minimum before convergence, basically, right? Your number of iterations are large. Suppose you talk about, let's say, 5,000 iterations to converge, then doing one iteration and moving ahead is foolishness, basically. Okay? But if it talks about only 5 iterations to converge, then I can talk about doing one iteration at a time, right? So that is the concept is called iteration unfolding, and it's actually very much buried here as well. So this is all about basic theory. Now we did not stop there, of course. We talked about several extensions, and first extension is flexible final time. So the final time need not be a priori fixed. That can be somewhere in between, little bit flexible and all that. So you have to compute the delta TF along with the delta U requirement. So delta U happens to the path and delta T at the final time. And both the adjustment has to happen together, and that is where you get a very tight accuracy, basically, very good terminal accuracy. And this is the approach that we use for this recent HSTDV launch vehicle kind of guidance, but it was actually not used in the real flight vehicle, but they actually use that for ground testing and all that, basically, before it flies. All right, now the parameterized MPSP is something that it is still one more extension, whether it talks about further improvement of computational time, smoothness of control history and all that is guaranteed as well. And then the next extension is generalized MPSP, where you can solve everything in continuous time framework without going to the discrete domain. Then you talk about tracking oriented MPSP. That means not only talk about terminal constraints and all, now we talk about output tracking as well. That we all know that inner loop control problems are typically tracking the outer loop control signal, basically, right? So that kind of formulation is possible provided you have tracking formulations, basically, right? So we have got a version where you talk about tracking MPSP as well. Then very recent, it is we talk about comprehensive MPSP. In fact, maybe today or tomorrow we are going to submit this paper. Almost ready to be submitted to IEEE. IEEE transactions. We'll take a try there. So this talks about generic cost function. Both each cost function can be both functions of state and control. And path constraints can also be included, this inequality constraints and all that. So the problem becomes pretty fair, pretty generic, basically. Right? There is almost no assumptions, no restrictions in some sense, basically. And this is where we prove this convergence also from a mathematical analysis, basically. That is not everything. We have extended it to impulsive MPSP as well. So that is where the control actions are impulsive. That one, you put a little bit pulse and then wait for some time, one more pulse, wait for some time, things like that. So there are many applications for that. One application happens to be in space, where you apply for momentary controls and all that and wait for a long time and things like that. And in fact, one of our paper we are going to submit it pretty soon, which talks about hollow orbit station keeping, which is in connection with the Aditya L1 mission that is coming up from ISRO. This is where we have used it in a very good way. You just use a little bit delta V correction and then wait for a longer time for error to build up. Then again a little bit correction and then wait for some time. Again a little bit like that. It's a little procedure. And this is actually very good use. And one of my earlier PhD students have actually used it for biomedical problem, where you talk about automatic therapy for cancer problems. Basically. Remember, radiotherapy, you cannot give it continuously. If you give continuously, then instead of curing the cancer, you will induce cancer actually. Right? So you have to keep a little bit and then leave it out, keep a little bit, leave it out, and like that. So that kind of thing has been used for radiotherapy as well, biomedical problems. Right? We very recently extended this idea to something called quasi-spectral MPSP, where we have got inspiration from some sort of our own MPSP idea as well as pseudospectral ideas. So this quasi-spectral MPSP happens to be even faster than our own MPSP, about 3 times more faster, basically, in a real good missile guidance problems and all that. So this is where now you talk about, well, MPSP itself was computationally very efficient, but by inspiration from quasi-spectral, and you want to keep on increasing the speed even further, and hence now you can even talk about putting this inequality constraints and then solving it through numerical ways and all that. So constrained quasi-spectral MPSP is still possible, and that is where our paper got accepted last week in ASME transactions, basically. One of these Journal of Dynamic Systems Measurement and Control. That is one of the very standard journals from ASME side. That's where your Kalman first paper appeared in that same journal, basically. Then we have, as I told before, little time back I hinted about it. We have also extended to something called uncentered MPSP, where the residual sensor errors and all that you can handle. And this is as it stands now, it is not capable of handling the time varying kind of difficulties and all that, time varying errors and all. But if the error happens to be time invariant, then we can handle it very easily. In other words, let's say you have got some constant parameters, but the exact value of the parameter is not known to you. Right? The parameter can be, let's say, you want the weight of a vehicle, but weight of the vehicle need not be exactly what's a 500 kg, right? It can be anywhere between 450 to 550, and the exact value you don't know. That depends on the loading conditions, right? So every time my truck gets loaded, I cannot go through a measurement and then find out the exact number and feed it to my, the truck computer and all that. That's really not very good, right? So those kind of problems we talk about doing it in an uncentered MPSP way. It actually given us very nice results also, basically. Then we are working right now in the formulation for DAE systems, which is called differential algebraic equations, differential algebraic systems. Essentially, part of the system dynamics is given by differential equations, but these differential equations state variables are constrained by algebraic constraints all the time, basically. One typical example happens to be like those of you are in aerospace, you can very quickly relate it to quaternion dynamics. All that you require is 3 parameters, but the differential equations are actually given in 4 parameters, Q1, Q2, Q3, Q4, but every time the constraint is the summation of all squares, like Q0 square plus Q1 square plus Q2 square plus Q3 square has to be equal to 1. no matter wherever you are actually. Okay? So those kind of constraints are typically valid, and also this is extremely valid, useful for under actuated systems. Basically. So those of you who are working on under actuated system will typically very quickly realize that DAE systems are a reality there basically. So now you see there are so many extensions, I mean so many variations, so many extensions and all that. Of course, not going to talk any of that. So those of you who are interested, you can read some of our publications, and there are many publications. Of course, you can talk about various things. These are all our own publications, but remember, many people have started working on that, and then there are the publication is the citations and all has gone more than probably I'll say 200 and all that. So many people have started applying. So I also will kind of invite all of you to apply. So this is one of our recent paper in a journal which talks about lunar soft landing. There's also on lunar soft landing. There's something like this the constant and nonlinear dynamic system. That's what I'm talking about. This uncentered MPSP sort of thing, what I've talked about here. This is the tracking version, TMPSP sort of thing. This is quasi-spectral without constraints, but with constraints also got accepted recently. I mean the path inequality constraints I'm talking about. And this is where you talk about this FFT, that flexible final time and all that. This is where we applied for a process control problem. And this is where you talk about air-to-ground missiles. This is where reusable launch vehicle. This is where you talk about air-to-ground missile again, but discrete MPSP, that other one was continuous. And here you talk about kind of interceptor for high-speed targets, essentially mid-course guidance for BMD, ballistic missile defense and all that. So there are many things. I'm not going to read in each and everything, but you have also used for reusable launch vehicle, long-range flight vehicles with solid motors like Agni missile essentially. And then we talk about I mean various different things basically. So I'm not going to keep on doing that. Now what happens if you just summarize everything? I mean, it has been used for missile guidance, surface to surface, surface to air, air to surface, boost phase, mid course, somatic phase, all sort of things basically. And these are all our own experience by the way. I've used it for launch vehicle guidance, both for high precision booster guidance as well as re-entry guidance for RLB. Used for lunar soft landing, it was used for formation flying of satellites, used for radar docking satellites and things like that. So I was thinking that we'll talk a little bit about lunar soft landing today, maybe about 10-15 minutes I'll spend about that before we stop. We'll stop at 2 o'clock roughly. And then we got about 20 minutes. So I will give you a small glimpse of that basically. So these are some of these people who have contributed heavily, and many of them are actually well placed now. Some of them are faculties in IITs, some of them are actually faculties in other places, some of them are doing postdocs in abroad. And these are very well established scientists there, which are actually contributing to the program AD, the ballistic missile defense program and all that. So they are all our own students from our lab basically. Coming to the guidance problem, there are also similar contributions. There are some directly scientists working from ISRO. And right now he is working on on the station keeping problem, and he just graduated. He's also from a scientist from ISRO, and he is just graduated and went to NL. He's a scientist in NL, and this visit went for postdoc just about 2 weeks back to Sweden basically. So this is something other than this, all of them are actually my previous students, but they are the ones who have contributed heavily. All right, now coming to the formation flying of satellites, I'm not going to talk anything about that because of lack of time now. So all that I need to tell here is we have written a book actually. And those of you are interested in this, you can actually think about seeing this book or having a glimpse of this book or whatever. And also probably you may think of having it in your library or whatever it is. It's published from going to be published from Pinjar. We have given everything to the press already. They have designed the cover page and everything is there. Maybe by end of this year, but early next year. Otherwise, I am expecting this book to be available. We have also given program files in MATLAB. So whatever results you see there is associated program files will also be available. We have discussed about 6 techniques, including MPSP and GPSP. This book is not about only MPSP techniques and all. We have talked about nonlinear dynamic inversion. We have also talked about adaptive control, augmented dynamic inversion. We have talked about MPSP, GMPSP, of course, then several things like that. So there are about 6 chapters, 6 different techniques and all that. We have also discussed a little bit about orbital mechanics and some necessary preliminaries so that we don't have to go for any other book and figure it out and then find out and come back and read and all that. Because it's a book after all, so So those of you are interested, you can see. But what is the summary part of it? Summary tells that MPSP happens to be far superior to LQR for circular orbits. And LQR, there are some concepts called circular orbit, elliptic orbit, and then highly elliptic, less elliptic, all sort of things. I mean, this goes to this space dynamics and all. Let me not get into that actually. But in general, MPSP happens to be far superior. And what happens is essentially LQR will work for circular orbits. That's not, see, circular orbits with less distance between leader and follower. The distance is small, and both of them are having circular orbits. That is where you can linearize the relative dynamics essentially. So the relative dynamics, if you linearize and then happen to kind of use your LQR theory, normally it does the job. But even if it does the job, the MPSP happens to be far superior, and there are reasons for that. We can see the book for that. But if it happens to be elliptic orbit, which is most of the cases, it will be elliptic. I mean, very perfect circular orbit is kind of an unrealistic thing. So most of the orbits will be typically elliptic, and especially if you talk about low Earth observation, right? The satellite comes very close to ground, takes some pictures and go away, and then comes back and things like that, and that is done for a purpose. Because if it continues in a low orbit and all that, then the drag will be more and satellite life will be less. So typically it is done in a very highly eccentric orbit where wherever you want to take a picture or something, you have to come very close to the ground, take a picture and go away. So you go out of the atmosphere all the way for a large part of this and then again come back and things like that. So that is where the elliptic trajectories are by design also. Right? So that is where you now talk about one after the other and things like that. Then you talk about doing in a linearized way, it is not going to work. Right? That is where you need to do this nonlinear optimal control, and MPSP happens to be lead to very satisfactory results for that. Okay. So we have also used SDRE approach. Those of you know about it, little extension of LQR and all that. But MPSP is comparable to an innovative SDRE approach, but it turns out that terminal accuracy is much better in MPSP. Control usage is also lesser in MPSP. And also this approach converges very rapidly, just within 4 iterations. Iterations are also given there. Then some final recommendations and all that, in which case you will use what and all that, that discussion also with there. So I'm not going to kind of advertise this book or propagate this book or whatever. I'm just telling you some of our experience that we have gone through. And he's just recently graduated. He's an ISRO scientist, just recently graduated and went back to ISRO for doing his work. Well, this book is not his thesis, by the way. Yeah, this book is I mean, almost done parallel to his thesis. His thesis talks about uncentered MPSP and then going and landing an asteroid and all that kind of problem. The lunar soft landing, asteroid soft landing, uncentered MPSP, those are part of his thesis. But he has contributed heavily to this book, which is actually resulted from one of my other earlier student, which was who graduated and went abroad for his PhD, and then settled in the US and all that. He was not participating in this book writing and all that. So. But the idea of the book actually originated from his work, but we have done substantial additional work to take this form of a book basically. So that is what the summary about. Now coming to the main part, which I wanted to talk today, this is something that interests kind of almost everyone in the country. So I thought I will just give you a glimpse of this lunar soft landing. Okay? This is especially we got deeply involved in Chandrayaan-2 mission for about 4 or 5 years. 2 PhD students, including, he himself contributed something, but there are also another PhD student who have contributed very heavily. Okay? So both of them have actually recently graduated this 4 or 5 months before. I mean, they all defended in some time 3 months before basically. So both of them have worked in a very good way. And he also has contributed a little thing as you go along, basically. It's as part of his master's thesis. His PhD thesis was very different, but master's thesis he actually did with me. And that point of time we started, and that is where he has contributed using GMPSP and all that. But anyway, so what is this lunar formation flying? We all know that this was the day that most of us remain awake, actually, right? September 7th, about a year back, year and 1 month or whatever. 13 months back, almost all of us remain awake, glued to the TV to see what happens, actually, right? That is where I was part of the ISRO. I was actually there in the mission lab and all that. They call it ISTRAC and all that. That is where our Prime Minister came and the ISRO chairman was there and all sort of things. A lot of excitation there. But we all know what happened eventually, right? We are there, but at the very end, we are not there, right? That kind of situation happened. But this is the mission, taken from the ISRO website. What happens there is your launch vehicle, which is actually GSLV Mark 3, which takes the satellite and throws in a lower orbit, and the launch vehicle job is done. After that, the satellite has a lot of fuel, so it actually does so-called Hohmann transfer and all that. So at this point, it will fire a lot of thruster for a small time, and it will go this called orbit raising maneuver. So this is go a little bit, go a little bit up, go a little bit up, and things like that. And then eventually it turns out that it will go through some sort of a transfer trajectory. And you do all these maneuvers and calculations in such a way that the time consumed is also critical. The moon was initially not there. Moon is also revolving on Earth, right? So initially the moon will be somewhere there. Now moon, by the time moon comes, takes a circle, revolves, comes here, he will also revolve and come here, right? So this calculation, time matching sort has to be very, very closely done. Right? That was all done properly by the way. Right? Now once you go there, meanwhile on halfway through somewhere you turn around. And remember, it's a space, right? So you can freely turn around. There is no drag or nothing there. So you can turn your vehicle opposite direction. And now we start talking about firing in the opposite side of the story. So eventually, what happens? You capture the lunar gravity will capture. It will be high eccentric kind of elliptic orbit, and then repeatedly you fire again to slow down. Here we fire to speed up. There you fire to slow down. Basically. So slow down. Eventually become 100 kilometer by 100 kilometer kind of stationary orbit there. There you spend some time and take some photographs and things like that to make sure that wherever you want to land, that is the site. And after that, the journey starts. And these are the three components taken again from ISRO website. We've got a rover and we have got this orbiter, which is still operational by the way, that has not failed. And then this rover is going to go inside the lander. When once the lander lands, it is supposed to this window is supposed to open, and then using the rails, this rover is going to come out, and then it's going to explore the lunar surface, send some data, blah blah, all sort of things basically. Right? So this part of the segment did not happen basically. But having said that, again, what was our task at that point in time? How to safe land this fellow on surface of the moon? That was the whole criterion. Only when you safe land this spacecraft about other things basically, right? So for that, as I told, it goes through 100 by 100 kilometer parking orbit, and then you do one last deorbit maneuver. One big, it is again going to reduce your orbit to quite a lot. So from 100 kilometers, you are all the way reduced to about, because the later part of the mission which is done is very different from this one. We got involved almost until the point where they changed the entire configuration, entire trajectory, everything was changed until the last 1 year actually, before the mission. So our involvement was typically kind of, you can say, up to 2017 sort of thing, 17, 18 like that. Okay? But between 18 to 19, there was the tremendous amount of change actually. So that we have not incorporated. All the results that you see is with respect to so-called previous configuration, not with respect to the final configuration which flew basically. Yeah, so that, let me take that as a disclaimer basically. All right, so that 100 kilometer to 18 kilometer, and then this 18 kilometer onwards, it is not instantaneous burning. It is going to be continuous burning from here. So continuously slow burning, very controlled way, you have to do that actually, right? So this is a segment which is very, very critical, which is called powered descent. But throughout the journey, you have got the thrust, and then thrust is getting manipulated. And depending on the thrust manipulation as well as the orientation of the vehicle, you will impart the braking mechanism both in magnitude as well as direction basically, right? So that is how the mission is going to be very critical at that point. And of course, this segment itself has several segments again, and there are several segments talks about, well, the phase 1, phase 2, phase 3, phase 4, phase 5, all sort of things. So phase 1 is braking with rough navigation. That means you don't know the exact the relative locations very accurately. You have spent a lot of time through the flight, through the journey. So the instruments will accumulate errors, and because of that, they are not too much reliable. Only star sensor will be reliable, but that only gives you altitude. INS system and all are typically not that reliable. And this orbit determination accuracy and all they are talking about, so that also leads to this inaccuracy problem. What matters eventually is finally what you see is where you land, right? So relatively a relative error between spacecraft and the landing site is all that matters basically. But that information is not available for 18 kilometer height. Your cameras are not good. So you come all the way to something like 7.5 kilometers, and then you kind of open up your cameras. And once you open up at 7 kilometers, 7.5 kilometers, you will see something basically, right? And depending on this modulation, I mean, these are all cataloged by the way. The entire moon surface has been cataloged. So depending on what you see below, you can actually talk about which crater is that, and depending on that, you can talk about what is your height and all that. Right? So that is actually a navigation problem, kind of done properly and all that. But the question is, because it's image processing thing, it is not going to give me instantaneous numbers. So I have to keep on doing that. I have to keep on doing that for some time, about 30-35 seconds. Then only I get some processing power, processing computational time I need for computing something which is reliable, basically, right? So this thing is continuous for some time, and that remember the satellite is not really stationary, right? It has got velocity, so it is not going to stay there forever. It is continuously moving, but you are just continuously holding the attitude, the orientation, and then it continuously kind of it just takes one picture and not as it's just continuously scanning. No, it's not continuously scanning. It just takes about one picture, and then for processing that you need the vehicle is traveled here, basically, right? So while you are here, you will actually get the information from here, and then you can, I mean, go back and recalculate that okay, if my height is something like that, how much height it will be, right? That kind of a thing. Because this to this is not a very long time and all that. If I know the accurate information here, I can actually predict what is my accurate information here. So that is what was supposed to be the mission phase 2 and all that. It's called attitude hold phase, and that is where once you know the very precise information here, depending on whatever relative information here, your phase 3 starts, and phase 3 starts happens to be very precision breaking phase. So that is where you do a very continuously, very careful maneuver and things like that to go to phase 4. And phase 4 is actually you remain vertical, and this y-axis is not up to scale, by the way. So the 7.4 kilometer that you talk about has become 100 meters. It's very close to surface of Earth. And that is where you open up another high resolution camera. Okay, that high resolution camera is going to scan this surface very well. And there you start landing vertically. And suppose there is a necessity of going to a different location because there may be some danger rate there, there may be some boulder or whatever there, then you can retarget it and go there, and that happens to be at around 20 meters. From 20 meters to 2 meters, you go again vertical. Okay, 100 meters to 20 meters, you can do some little bit maneuver and retarget yourself. That is terminal descent, and from 20 meter to 2 meter you just go again vertical just to make sure that you are perfectly vertical, and then any attitude corrections and all that can happen during that time. And for 2 meter altitude you simply drop. There is nothing like touchdown slowly and all that. The reason being, if you don't stop your engine at some height, then your engine plumes are there, and that engine plume is going to hit the moon surface, and there may be some dusting and all that. And once the dust comes out, and it kind of clouds everything. And remember, these are solar panels for generating power and all. Once the dust coverage is there, there is no wind and no water, nothing there in the moon, basically, right? Once the dust is there, it will stick to that. Okay? Then your solar power generation will be compromised, basically. So because of that, at around 2 meter altitude, you just simply drop it, basically. Okay? So that is what the phase 1, phase 2, phase 3, all that happens. And then our contribution was largely in this segment, which is phase 3 and then phase 4 sort of thing. So we have done several contributions. I'm not going to get into that. I mean, there are many things, and this first thing is I'm out of a small part. If I want to talk about, then I talk about MPSP guidance here, and eventually we recommended minimums of guidance here, by the way. So again, of course, because we did the work in guidance control, integrated guidance control on all segments, say phase 1, phase 2, phase 3. I mean, phase 1, phase 3, phase 4, like that. Both explicit, non-explicit, inverse polynomial, many variety versions. Control design again using 6-stop simulation, nonlinear control design using DI, dynamic inversion, robust adaptive intelligent design, which is using some neural networks and all that. Then we also propose some cluster selection logic and things like that, and eventually some IGC as well. So out of that, if you talk about, of course, there will be several publications. This list is not exhaust. We are still writing a lot of journal versions of all this. So, but I mean, obviously, if you do so much of work with 2, 3, I mean, about 4 years, 5 years, and things like that, obviously, we'll do pile up a lot of work with that. So these are some of these publications already there. If you want to kind of see what is going on, you can see some of these publications. But eventually, the ideal guidance algorithm should ensure, I don't know, the list is enormous actually. Okay, so if you really talk about segment 3, which is like precise navigation, it will go slowly and then become perfectly vertical here. So yeah, the requirements are many, basically, right? I'm not going to read through that because of lack of time, but you can see many of that. Now the question is how much of that you can actually do, basically, right? So there are various guidance laws which can do only a little bit. This issue number 8 or whatever it is, like that kind of a thing. All the things doing is actually very difficult task to do, basically. So this is something that we started the journey. We took some sort of a dynamics that is there. Remember, there is no atmosphere, so that means there is no aerodynamics. But if you're talking about lunars, kind of moon is, I mean, moon is actually a sphere. It's not a flat surface. So we can actually talk about spherical moon and things like that. That will give you some sort of a nonlinear equations and all. So we started doing all that, and hence we put this nonlinear MPSP. And then we talked about somewhat fuel optimization in the process, and eventually it leads to that kind of a cost function. But I mean, equivalent, you can talk about that. Even though this is not one-to-one, but it leads to some sort of a close to fuel optimization algorithm, basically. And fuel optimization is very critical, remember, because you cannot do the job with a lot of fuel. I mean, lot of fuel means it is payload to the satellite, and satellite itself is a payload to the launch vehicle. So a lot of fuel means your satellite weight will be a lot more, and if the satellite weight is lot more, your launch vehicle capability has to be there accordingly, and you may not be able to lift off also, basically. So that because the launch vehicle may not be able to handle that, basically. So this is very critical to have some sort of a fuel optimal solution. So I've done this mathematics part again. I'm going to skip it through. You can see some of these the results which are very tightly there, about 20 meters altitude. That's what you're talking about. So you can see very. I mean, no matter where you start, it eventually goes to this 20-meter altitude very nicely. Similarly, the velocity part is turns out to be zero. Radial velocity, translation velocity, both of them at 20-meter altitude. No matter whatever is the initial condition, they will all turn out to be zero, basically. Similarly, thrust and then altitude. Now you see that there was a problem with that. In other words, your beta, which is the look angle, the thrust angle, and all that, which is supposed to be 90 degree, but it has become close to 90, but really not 90. Right? It is still left out with some 95 degrees and all that, basically. Some 5-degree offset and all that is happening. It can be handled in a different way, but then we are not happy about kind of what our algorithm did. I mean, obviously, it was not able to do the great job that we wanted to do. And that point of time, we latch on to some literature here, and this is actually Chinese people. I mean, they've actually implemented something on the same problem, but not only that caught our eye because of the title and all that, but it also caught our eye because they have actually used NPSP. So they've actually used that. So we thought, okay, we can also use that, right? So now we went to but they've used linear sense. We have used nonlinear sense. But we got a little bit inspiration from there and all that. We went to this jerk-based NPSP in some sense. In other words, your acceleration also becomes some sort of a acceleration is not a control variable anymore, but acceleration becomes state, and rate of change of acceleration becomes control. The reason behind that is the moment you talk about control variables, you cannot talk about hard constraints. You have to live with soft constraints. But if you treat that as a state constraint, then you can talk about hard constraints. Hard constraints are applicable only for states, basically. States or output, whatever. Control sync has no meaning of hard constraints. So all that we resolve that, and again you can now you can see that okay, after you do all that, it turns out to be very nice actually. Now you talk about, well, my beta is now no more 95 and things like that. It actually goes to 90 degrees. You can see the 90 degree here and 90 degree there, right? So this is the line that you're talking about, red line and all that. So that actually gives you very closely. And of course, you have also on the way you have compared with so-called Apollo guidance, very old guidance and all that, which actually eventually ISRO implemented that. Then CT, which is a constraint terminal vector guidance and all that. So that is another one which is actually developed from NASA again. But it is not very suitable because the terminal constraint will be 96 degrees and 98 degrees like that. It's not nowhere close to 90 degrees, right? Because it does not talk about acceleration constraint. It leaves the problem at velocity constraint only. Right? So there are details into that. I'll not get into, but ultimately, even the comparison sense, it turns out to be this is best actually. All right, let me now get into that too much. And again, not only the segment 3, but we also applied in segment 4. And eventually, even if you start vertical, because initially it is vertical, it is going to go through retargeting, no matter wherever you find it. But eventually, it will get you vertical also, right? So this is the actual simulation result what you see there. Then the question is whether it is applicable in real time or not. Then we'll answer to some sort of a publication which talks about current space grade processors as well as future space grade processors, and these are some of these available processors right now. And our ISRO processor is kind of lesser than that, 64 megahertz actually. That kind of, as long as I remember actually. It operates on 64 megahertz. But these are something available, and this is something like future processors and all, which is also available in the high grade. Now, what we have done is we assume that it is going to be 1 gigahertz, and then we do some sort of a PIL simulation and all that using this Texas Instrument, Texas Instrument processor, whatever we can talk about. So this is the DSP processor which operates on 456 megahertz. It's not really 1 gigahertz and all that, but you can always do this scaling up, scaling down based on the computational time that comes out to processor A to processor B. And this processor we selected because this is the one that was selected by Team Indus. Those of you remember, small company, Team Indus was doing a parallel mission sort of thing to go to moon. They were participating in this lunar X Prize competition and all that. And these are the only three companies got finally listed. One is US, one is Israel, and one is India. And in fact, our company could not gather sufficient funds for the launch, so they could not launch. And meanwhile, the X Prize was withdrawn because none of the companies could actually launch privately. So the X Prize was not given to anybody; it was withdrawn completely. And that company is not there in a way because the company got disintegrated in some sense. Basically, they are talking about doing some other problem, some other solutions right now. But at that point of time, they were talking about this processor, so that we got about this processor because of that basically. So this we do that, and then we can execution time, you can scale up, scale down, all sort of things. Then it turns out that well, if you really talk about just about 1 gigahertz processor, and which is not really unrealistic to demand, because future processors can go all the way to 2.9 gigahertz also. So that is what you are assuming just 1 gigahertz basically, and with that it is possible to do. That's what the bottom line is. If you give us a 1 gigahertz processor, then this MPSP can be done. Basically. That's the bottom line. So that's why written processor clock with 1 gigahertz frequency is enough for online implementation. Basically. That again depends on your delta T that you talk about. The guidance cycle time, cycle time update basically, right? So delta T for guidance, it depends on that. And typically it is about, 1 gigahertz. If you see it, it doesn't talk about 21 milliseconds, 90 milliseconds like that. It is. So typical operation time is about 200 milliseconds. All right. So if you see that this CTVG, MPSP, JMPSP, well, this happens to be like this. So this is polynomial. Turns out to be NASA based. That's what it happens. But somewhere you will see the cross mark. But you see JMPSP turns out to be the tick mark everywhere, right? All the things that you talk about here can be obtained through our formulation there. Now the question is, this is not everything. There are several other criterion that we talked about, right? I mean, this is not only 3 criterion. So you go back to that and resolve this problem this is not MPSP, this is something different, but I just thought I'll give a glimpse of that as well. So you go back to all these conditions and try to satisfy more and more and more. The linear problem is actually not a bad thing because you are very close to the where you want to land basically, right? So if you just about downrange of about 5-10 kilometers away, the moon curvature is not much. So entire thing you can talk about like a flat earth sort of thing. You can take about like any city, for example, right? If you talk, not only the full city, by the way, that just about a city diameter will talk about something like 30-40 kilometers. So now you're talking about just about 5-10 kilometers away. So that 10 kilometer radius, if you talk 5 kilometer radius, if you talk about, or 10 kilometer radius, if you talk about, the land is typically flat. So with that, if you talk about system dynamics, it becomes linear. And using linear and all that, you can do several things basically, right? You can do closed form solution, you can do final time computation, you can do many things that has happened there. And eventually, this is what we strongly recommended to ISRO because this actually led to closed form guidance law. This is not computational. The MPSP happens to be iterative, but this actually is not iterative. This is a perfectly closed loop, actually, right? You can directly get a closed form formula basically. And that also has additional advantage. We are now talking about explicit way of computing final time, explicit way of avoiding ground hitting, all sort of things there. So there were a lot of stories for that, but we recommended that strongly basically. But eventually, if you see that why we recommended strongly, now not only these 3, but we put 3 more conditions there. And no matter what, you have in our own MPSP, JMPSP that I talked about, only first 3 are tick mark, but these 2 are not really tick mark, right? These 2 are actually wrong. So that means it does not avoid this ground collision and explicitly, of course, it certainly doesn't give you a closed form expression for guidance command. So now if these 2 also becomes a these 3 also becomes a reality, then this happens to be true basically. Okay. So this is what we do. Okay. That is why we recommended that. And there was a nice car analogy that I thought about that one time. Well, if you go back to 62, I don't know how many of you are born by that time. I myself was not born, by the way. And that is where this first lunar Apollo missions and all that happened, right? So around that time. So that is the time period where we are talking about Fiat Padmini and all that. That's that kind of car. Which was a luxury model at that point of time. It is lovable now, but it is that was the car of the moment at that point of time. Right? Everybody wanted to have dream car sort of thing. Then fast forward to 98, you got this kind of a things. Our legendary Tata Indigo and also Tata Indica and all that. And then we got this 2018. Now you can talk about very luxurious car and all that there. So if you just talk about this guidance law point of view, there are 3 things that we talked about: Apollo guidance, CTVC guidance, and our own minimum observed guidance sort of thing. And this happens to be around that period of time, and this happens around that, and this happens around that basically. Now, of course, this is not a choice because it doesn't give CTVC guidance, doesn't give you the final latitude constraints and all that. So that doesn't happen to be a choice. Now, the choice between these two, whether you go back and select that or you become a little more bold and select this, basically, right? And unfortunately, despite our lot of struggle, lot of push and all that, whatever I could do maximum, eventually ISRO selected this. Okay, and that is because of the legacy, and then there are some. I mean, I'll not tell you some inside stories and all that, but there are people in general in space industry. They want to be extra conservative, basically, right? So they told, okay, this is something that ISRO, I mean, has flown before and things like that. So we'll go with that. But you have forgotten that NASA has actually gone with in a when the vehicle was completely, or the spacecraft was very close to the surface of the moon. There were astronauts inside, and that is they were the actual thing they were actually. And number one. Number two is they went to a location of the moon, which is actually pretty safe. In other words, it was kind of a desert land, basically, right? If you happen to go very close to equator, about 30-40 degree latitude, then it will get a lot of land, flat land like that. Our ISRO's mission was close to South Pole, rather, which is the terrain is hazardous. Actually. The bottom line is there are no pilot, right? So everything has to be done in autonomous sense. So selecting that way back 1960s guidance, even though it apparently extremely simple to understand, any high school fellow can understand it. That is that simple actually. And it doesn't just talk about just one slide to explain what is the concept there, but I'll not get into that. But that is what eventually ISRO selected. And unfortunately, of course, I mean, it's disheartening to see that eventually the mission was not successful. So now they are talking about Chandrayaan 3, and they are actually relooking this 2018, our own minimum observed guidance, in a very closely. In fact, I don't know what is the progress there. They have not informed me yet. But I hope that there will be enough confidence now to get into this our proposal, what we propose as minimum observed. All right. So concluding remarks. I took a lot of time of yours. Some concluding remarks finally. Nonlinear optimal control in real time. That is what we are talking about. So of course, efficient algorithms are the key, which has to close the gap by 70%. But you would also take advantage of high-grade processors. So that's going to be a good, nice answer. So even though nonlinear optimal control is extremely powerful for solving a variety of difficult problems, it suffers from computational complexity issues. That is the very bottom line that you need to remember, and that is why it has not become omnipresent yet, right? Because a lot of people found it, oh, this is very good, and you can solve a lot of things, but I cannot use it in real-time simulations, real-time applications. Doesn't mean that it is useless, because you can still talk about trajectory optimization, right? For example, if you want to talk about which point of the time the launch vehicle has to take off so that it will go there and some point of time later and things like that. So that is how it is, right? Which point of time and which path I'll take and how many orbit range maneuver I'll do so that I will go at a point where the moon will be there and things like that. That decision doesn't have to be real time, right? You can take your time and do it offline studies and all that. Right? So those are called trajectory optimization and all that can still be applicable. But now we are talking about online trajectory optimization, guidance and things like that. Whether that is applicable, certainly not, right? So that is the computational complexity point of view. Okay? Now, trajectory optimization problem solved in real time using onboard computers leads to very powerful computational guidance, of course. And remember, this computational guidance has gained a lot of importance in literature. In fact, it is so good promise that IISc, Journal of Guidance Control and Dynamics, which happens to be a very prominent journal in our field, which came up with a special issue on computational guidance and control in 2017 itself. So this has gained attention all over the world. And now people are realizing that traditional way of doing guidance problems using struggling with a lot of geometrical issues or some sort of a kind of inspired way of putting a formula here, formula there, and things like that, and then doing some sort of analysis with a lot of assumptions and all that may not be actually a good idea. You go straight into optimal control, formulate that in that sense, and then talk about solving that in a computational way or whatever. Then get to powerful guidance law, right? That is the line of thought that happens, and that is the line of thought actually happening in CPS also, cyber physical systems. We talk about autonomous ground vehicles. Now we are talking about MPC way of solving and all that, right? I mean, this is the direction that the world is going basically. Right? So this is the computational guidance is the need of the hour, and it's going to stay for future as well. Now the processor is not going to go back, right? Processor power has come. It is going to be more. And now people talk about quantum computing. It's going to be even more, right? So now your algorithms are also better and better and better. Then your delta T of guidance cycle update can be smaller and smaller and smaller. If it is smaller and smaller, then you can now talk about aerospace applications and highly sensitive problems, all sort of things you can talk about now. So it's better that we understand this efficient algorithms in a better way, basically. And this MPSP idea happens to be one of the contribution in that side of the story, basically. All right. Continuing last concluding remarks, MPSP happens to be a very highly promising nonlinear real-time optimal control design technique. It facilitates computational guidance, in fact. And various extensions of MPSP designs have already been developed. We've got this PMPSP, GMPSP, IMPSP, TMPSP, QSMPSP, GCMPSP, UMPSP, architecture, right? So it continues. In fact, we are trying to write a tutorial paper in IEEE Control System magazine now. It may turn out to be, I mean, sometime next year it may come, basically. So let us see how it happens. There's a specific exclusive edition that I'm planning to propose for space applications only, and part of that it may happen actually. There is a long-term plan of writing a book on MPSP itself, but I don't know how long that will take. It may take 3 years, 4 years. I have no idea actually at this point of time. Then various. By the way, we are actually talking about developing a software now. I mean, one of the master students is actually working on putting all these algorithms in Python coding, and then this Python coding will be available to any user with some licensing and all that, like any other software, basically, any other traject optimization software. We'll talk about fast traject optimization as well as guidance problem. So the name of the software that we are thinking about is traject optimization and guidance combined together. We talk about Tropidence, basically, traject optimization and guidance, Trop and then dense, basically. Tropidence we are talking, and some name can be given different, I mean, as it evolves. But the journey has already started. They're trying to document everything in a better way, putting that everything in Python, and then various different classes will happen. Appropriate APIs will be given, user interface will be given, GUIs will be there, all sort of things, basically. So let us see how it develops, but we are very strongly hopeful that it may develop towards a good optimal control design software itself, basically. That should be available in a year's time. If our journey continues in a good way, it will happen in a year's time. All right. So various challenging guidance problems for aerospace vehicles has been solved and currently being solved as well. And one of the examples that I gave you is our Aditya L1 mission, where we are actually using IMPSP and then solving it right now, basically. Then this DI system is actually under development. It is not yet published and all that. So that kind of things are getting done. And many things have been done, many things are being done, not only by us, but there are various other people from, mainly from China, and then some people from Italy. Some citations we have seen from Korea, some citations from UK, and limited sense in US as well. So these are some of the places where aerospace problems are getting a lot of highlights and all that. Right? So that is where it is evolving globally in some sense. So MPSP has evolved as a benchmark technique for ISRO and DRDO as well. Now they are not gone to something that bold that they can fly it, but whatever they are flying, they are actually comparing that with MPSP and then telling the about tuning is good or very close or whatever it is, right? So before flying in using some other guidance and things like that, they are actually taking it as some sort of a benchmark and then trying to compare their results and then trying to go ahead and fly with the other one. Okay. It actually helps them in tuning the other methods very well. And also just for information, because I'm talking here, this IMPSP technique is getting evaluated to be used in this space docking mission of ISRO. Now that because of the COVID, everything is getting shifted and all that, so every program is getting delayed. But that is where they are doing some experimental testing also inside ISRO, basically. Okay. So MPSP is gaining good acceptance in worldwide. That's what I told. We have got citations, of course, from our own country, but we have got China. One of that I've already shown you is part of this talk. People from South Korea, UK, US, and Italy also they've used, and they're actually doing very nice extensions also. It is just not there. We are proposing techniques and they are using, not like that. They are actually going and digging out further and doing it various traditional optimal control, and then how this gels well. They are finding correlations, proofs, and extensions and applications, things like that. So there's momentum has already started in a very good way. So I invite all of you, those are interested in optimal control, to join hands and then explore this field also. So with that, probably I'll stop here. Sorry for taking longer, almost 15 minutes longer than expected. Thank you. Thanks for your attention.
Thank you, sir. We were really privileged
I'm
to
done.